Okay, so what I'm going to try to do is automate this circuit, and the key here is to identify that every time I'm clicking things on the screen here, all I'm doing are effectively toggling digital signals. So, I mean, clearly the input B here is an 8-bit digital signal, but so is this B select. It's just a 0 or a 1, right? Same for this store button. This is just making this as outputting either a 0 or a 1. That's controlling whether or not my accumulator is storing a value. And so what I can do, you can kind of ignore the circuit a little bit on the left here. On the right, what you can see what I'm doing is I've got the exact same circuit as before, only instead of having sort of buttons and bit fields and switches that I'm controlling with my finger, I have this thing like here called immediate 8, which okay, on the left you can kind of see it's just an 8-bit signal store A down here that's controlling whether or not my accumulator is storing a value. That's just it's a digital signal coming from somewhere. So as long as I can generate the appropriate digital signals, I can effectively control this calculator with electronics. And so we'll get to the circuit on the left in just a second. What I want to do though is take a look at how we might do something a little useful with this here. So let's say we just want to do something simple, like we're going to add two numbers together. So to start with, what I might do is I'm going to say I'm going to put the first number that I want to add. I need to put that in the accumulator, like we saw in the previous video. So to do that, I've got all my signals here in this table. I'm not storing anything to RAM, but I do want to put something in my accumulator. So that bit here is a 1. B select is a 0 because I want to get a value from this immediate field. Subtract is a 0 because I don't want to subtract. I'm gonna add. I'm gonna assume the accumulator effectively starts as 0. So 0 plus whatever number I enter, it will be the number that I want in the accumulator. And we'll say the first number I want to enter is 5. So I'm going to put that here in my immediate 8 value should be a 5. And then address, which is controlling where in memory I'm storing something, is basically not applicable because I'm not storing anything yet. So we can set it all to zeros. To just as placeholders. So after basically I configure these signals with this pattern, I should get and the clock ticks once, right? Then I should get the value 5 in my accumulator. Okay, so let's say next I want to add my second number to that value that's in my accumulator. We'll say it's 4 that is the one that I want to add. Okay, so then similarly to before, I'm not storing anything in RAM, but I am storing something in my accumulator. I'm going to use a value that's in the immediate field, and I'm adding it. I'm not subtracting it. The value that I want to add is 4. The accumulator had 5 to begin with, so the result of this should be the accumulator 5 plus the immediate value 4, and that should put the value 9 in my accumulator. Again, the address can be 0. And then lastly, let's say I just want to, I want to exercise a couple more parts of this thing. So I'm going to store that into my memory, specifically in memory address 1. So now store RAM is a 1 because I'm trying to put something in that memory location. I'm not changing the accumulator. Now it doesn't really matter what B select and sub are because I'm not really performing any operations with my ALU at the same time. And similarly, it doesn't matter what my immediate field is. And now the address does matter. I want the address to be 1, and then when the clock ticks, the value that's in the accumulator, which should be 9 at this point, is then stored into memory location 1, the memory location specified by this address. And so hopefully at this point you can see this is the pattern that I would sort of set these signals to be in order to achieve this little series of steps. And so what we can do is take a look at the left part of the circuit to see how we can do that. And in reality, it's actually quite simple. So what I've got here is just a block of memory, or a ROM in this case. And so each, you can see here, I've got, it starts at kind of 0. This is memory location 0, memory location 1, memory location 2. And if you take the time, you can convince yourself that like this number here, this whole string of zeros and ones, is stored in memory location 0 as this number here. 0, 1, 0, 0 is 4. 0, 0, 0, 0 is 0. 0, 1, 0, 1 is 5. And this is 0. So this should be 4, 0, 5, 0. And that's the value I have stored here. And so when this memory piece of memory is outputting the value of memory location 0, then that value goes on these 16 digital signals. And you can see here that those signals are set up just like the way we wanted to in order to store the value 5 here into the accumulator. Store RAM is 0, store A is 1. I'm adding, I'm using the immediate field, the immediate value is 5, address is 0. So, so basically what I can do is, as long as I can figure out a series of, what are the zeros and ones that go to each of these signals in order to do what I want, I can store those in just a spot in memory. And then on the left of this memory here, the thing that's selecting the address is just a simple counter. So this is going to start at 0, and then on every clock cycle, it'll increment by 1. So that just automatically goes from one memory location to the next, which is effectively one instruction to the next. And so what I'm going to do here is toggle my clock a couple times to kind of show you this in action. So I'll see if I can kind of grab the memory locations and just enough of my calculator that we can see what's going on. So I'm going to toggle the clock once. And so on that toggle, you'll notice that the value 5 was loaded into my accumulator. On the next clock cycle, I move to this next instruction, which should be adding the value 4 to this in the accumulator. If I toggle my clock, I get the result of that, which is 9. And then if I toggle my clock one more time, I go to the next instruction, which should be storing that value. If I toggle one more time, you'll notice that the address has the value 1. At that location is the value 9, which is the value of my accumulator. So this little sequence of events was able to do the very simple thing that I wanted it to do, which was just add two numbers together and store it in memory. And the way it was able to do that was just by taking all of my buttons and switches and bit fields and making them, sort of packing them into a memory location, and using a counter to automatically go from one memory location to the next. Okay, so to summarize, what we started with in the previous video all the way at the beginning was a very simple circuit, a little ALU that did addition and subtraction. And then by adding a couple of things, namely we added some RAM, we put a 16x8 memory cell in there to do some useful stuff. We moved one of the registers or one of the inputs down underneath the ALU to be an accumulator to kind of simplify our final step. And then what we did is sort of pack all of our switches and signals and bit fields into a piece of memory and assign a counter to just automatically increment from one memory location to the next. What we effectively got was this circuit on the right here, which we just saw is able to add two numbers together and store it to memory all on its own, which seems pretty simple, sure, but if, in reality, that's the basics of a computer. Hopefully you can kind of see how, with a little bit of creativity, we could start to write programs effectively for this calculator that can do things like not just sort of add and subtract, but maybe multiply or divide or compute Fibonacci sequences or things like that. It's not quite a full computer yet. If you watch or after this take a look at the Turing Machines video, you realize sort of what's missing here. But it's getting pretty close, and hopefully at this point you can kind of see how the little bits and pieces that we learned in EE360 and digital logic come together to start to make what we know to be a computer. And in fact, the rest of this course effectively will be on sort of doing this same process, but on a device that will be a fully functioning computer. All right, today's quote, forgive me, is a little long one, but it's a great one. It's from Theodore Roosevelt, who said, "It is not the critic who counts, not the man who points out how the strong man stumbles or where the doer of deeds could have done them better. The credit belongs to the man who is actually in the arena, whose face is marred by dust and sweat and blood, who strives valiantly, who errs, who comes up short again and again, because there is no effort without error and shortcoming, but who does actually strive to do the deeds, who knows great enthusiasms, the great devotions, who spends himself in a worthy cause, who at the best knows in the end the triumph of high achievement, and who at the worst, if he fails, at least fails while daring greatly, so that his place shall never be with those cold and timid souls who neither know victory nor defeat." I'll see you next time.